So here's an example of a conservation of energy problem we're going to learn how to solve. Before we put anything down, there is a crucial fact to remember. The problems will tell you information about speed, about height, and about compression of a spring. Whenever there is speed in the problem, you have kinetic energy, which is equal to 1/2 mv squared. Whenever there is an object with a height above a zero level, you have potential energy, and it's gravitational potential energy. So mgh is the formula. Whenever you have compression, there's elastic potential energy, and the formula for that is 1/2 kx squared. By the way, the units for k, if we haven't seen that yet, the units for k, the stiffness, are newtons per meter. Some objects, you have to exert a big force to get it to compress 1 meter. Other objects, you have to exert a small force to get it to compress 1 meter. So this is a measure of how stiff the object is. How much force do you have to put in to compress it by a meter? Okay, so we've got this. Now let's read the problem and look for speed, height, compression. A 5 kilogram child is at the top of a 3 meter high frictionless slide, starting from rest. Wait, 3 meter high, that's information about height. Then it says, starting from rest, the child goes down the slide, speeding up. Aha, we gain speed. A, calculate the child's speed at the bottom of the slide. And then B, describe the energy transformation that occurs as the child descends. Here's the picture, and this picture is likely going to be given to you when you solve these problems. Got a child going down, and here she is at the bottom. Our first task is to label initial and final. The child is up here at the top initially, that's our initial moment, and then we're going to compare that moment to the final moment when she's down here at the bottom. So she's here, and then a few seconds later she's down here. She goes down. Initially, and then last thing, we have to establish our zero level. The most convenient location for zero level is the bottommost point that the object reaches. So let's use that rule in this case. Here's our zero level. I will measure height up from that blue line. Okay. At the beginning, initially, what does the child have? Does she have speed? We'll know because it says starting from rest. There's no speed, so I don't write speed under initial. Does she have height? The next one in our list. Yes, she's 3 meters up. So let me write down h, and that's the initial height. Hi. Okay. So we checked this. There's none of it, so we didn't write it. We have some of this, so we write it. What about compression? Well, there's no spring in this problem, so there's no compression. All she has at the beginning is height. At the end, does she have speed? Well, she speeds up, and we're asked to find the speed at the end. So I would say yes, there is speed. Vf. I put an F because that's the final moment. What about, so we checked speed, what about height? Do we have height at the end? No, we are 0 meters up from the ground. At the beginning, we were 3 meters up from our zero level. And here, how many meters up are we? 0 meters. Okay, what about our last thing, compression? Nope, none of that because there's no spring. So initially, we have height. At the end, we have speed. As she goes down, she loses height and she gains speed. So look at this big equation. We don't write the entire thing. We only write down the part that applies for this equation. She doesn't have speed, we said, initially. She doesn't have compression initially. So when I equate her initial energy with her, when I go and equate her initial energy, with her final energy, what do I put on the left side? I only put the energy associated with height, just this term right here. mgh initial. On the right side, what can we say? She has final, final speed is all. So I don't put mgh final because she doesn't have final height, it's 0. I don't put this term down because she doesn't have final compression, it's 0. There is no spring to compress. So all we have on the right is the energy associated with speed, kinetic energy. And its formula for kinetic energy, 1/2 mvf squared. And then from here we solve the equation. If you want, you can divide both sides by 3. Remember that each side of an equation has invisible parentheses there. So when you divide, did I say by 3? By m. You can divide both sides by m. And the reason is because then the masses cancel out. This cancels here, and over here, let me use a different color. Right. Over here, this mass cancels as well. And now we know g, it's 9.81. We know her initial height, it's 3. You solve VF. It's going to be the square root of 2 times 3 times 9.81. And what do we get? I believe this comes to 7.67 meters per second. And we're not really worrying about sig figs. An interesting thing to point out is it doesn't matter what the angle or shape of the slide is. If the shape is really, really steep, she'll have this final speed. If the shape is really shallow, she still has this final speed. It doesn't matter, which is kind of interesting. The last thing for us to do is talk about the energy transformation that occurs. She starts with what? What does she have at the beginning? And I'm not going to put down elastic potential energy because there's none of it in this example. She starts with just height, therefore just gravitational potential energy. She doesn't have any KE at the beginning because she doesn't have any speed. At the end, the final moment here, what are the energies that I should draw in a bar graph? Well, she has speed, so she has kinetic energy, and that's all she has. So what happened to the energy? We started out with this, and we converted it into this. So for part B, we would say PEG transformed or converted into kinetic energy. The last thing that I want to consider is the energy transformation in this specific case. There's a skier who's traveling at some initial speed VI. She's at the top of a slope, so she has height, and we'll measure her height from this 0 level, from the bottom of the slope. So from that red line, from that 0 level, we go vertically straight up till we get to the skier, and then we stop at the skier, and that's her initial height. At the bottom, her final height is 0 because she's at the 0 level. She's 0 meters up from this red line. Okay, as she goes down, she speeds up. And so when she gets to the bottom, she is moving at a faster final speed. What happens? She loses height as she goes down, right? Because when she's right here, she has even less height than before. So the height has decreased. And right here, the height decreases, and it keeps going down. And what is she gaining? She is gaining speed. So if we make our graphs, she initially has potential energy, gravitational, because she's really high up. And she even has some kinetic energy. At the bottom, at the end here, she has lost all of her initial height, so there's no gravitational potential energy, and she has gained, she had this initial kinetic energy, and that's still there, but then we've also transferred the PEG over as kinetic energy, or into kinetic energy. So she has more total kinetic energy here than she did at the beginning. Where did it come from? It was transformed from PEG. So what we would say for the energy transformation in this case, we would say gravitational potential energy is converted into or is transformed into kinetic energy. And that's true even though she has some kinetic energy to start. This part, this little bit of kinetic energy, does not transform. She maintains that part of the speed of the energy as she goes down.